So here we go. Oh, sorry. All right, the beginning of this video is super awkward. So I'm going to title this More Methods of Integration. And also, just as a heads up, next unit, guess what we're going to do? More ways that you can do antiderivatives. So just as a foreshadowing. So more methods of integration. Thank you. So I'm going to write up here your patterns for the inverse trig derivatives. When I write them up, you're going to look at them and go, oh my goodness, what on earth is that? But then I'm going to explain them to you and you're going to calm down. This always goes well, okay? But it's going to look like the alphabet threw up on your paper for just a second until I explain to you what's what. So let me write these and then you can write them down. There's only 3 of them. Yeah, once we do a couple of these, it will probably come back to you.
This is a drill. This is a drill. This is a drill.
All right. All you really need to be able to do is identify these. You really don't need to memorize the left side of the equal sign. You just need to be able to tell which one is which. So how out of the 3 would you identify arctangent? Like what's different about that one? It doesn't have a square root. Also, it's adding. I would go for it doesn't have a square root. All right, that's arctangent. And then how do you tell the difference between the other 2? Yeah, one's A first, one's U first, and arcsecant has like an extra little doodad out front. Okay, so you just have to be able to tell which one is which. These are all essentially the same. Look, arcsine U over A plus C, arctangent U over A plus C, arcsecant U over A plus C. They're all really the same. The only difference is arcsine does not have that fraction out front. Arcsecant has an absolute value. I will not take off if you forget the absolute value because like for heaven's sake, but you get that they're all the same. So all you really have to be able to do is identify them. And I'm going to kind of speed things up and keep this going here to make sure we can finish. All right. So stick with me here. If I do anything too quickly, just yell. So as you're writing that, just think about which one of the 3 do you think it is? Just matching up the pattern. Do you think it's arcsine, arctangent, or arcsecant? It's arcsine. It's got a square root and there's not a little doodad out front. If this was multiple choice, you'd probably be able to just pick the answer. It's the one with the arcsine in it, unless they were evil and made 2 of them have an arcsine, in which case you'd have to actually do the problem. But you get what I'm saying? Like, you really just need to be able to identify. A is always going to be a value. U is always going to be a variable. So A takes the place of a number, U takes the place of the variable, which is X, all right? So A is gonna be 8. How did I get that? Where did I get 8 from? Yeah, 8 squared gives you 64. U is gonna be 3x. You square that, you get 9x squared. They're gonna pick things that are perfect squares, but let's pretend it wasn't for a second. Let's say there was a 7 in there. Then you would just make it square root of 7, okay? Then you have to do the problem like a regular U substitution. The derivative of 3x is 3, and we're going to adjust that with a 1/3. So that part, like this right here, doesn't change. That's the same as what we've been doing. And then you can pretty much write out the answer. Let me zoom in a little bit more. You're going to have a 1/3 out front for this adjustment that we made. 1/3. We said it was arcsine. Arcsine doesn't have anything in front of it, so we don't have any other like coefficient to put. It'll just be arcsine u over a, which would be 3x over 8 plus c. And so essentially you just write the answer. So they look scary at first, but these are actually not that bad. In fact, people kind of like these on the test because if you recognize the pattern, that's really all that there is. Let's try another one. So again, which one of the three would that be? Yeah, and so if it was multiple choice, you would just pick arcsecant. Hopefully they wouldn't make two of the choices be that and you could just get the answer. All right, A is going to be a value. U is going to take the place of the variable. So what is A going to be for this? U is going to be 4x, and then A is going to be 3. Good, 3 squared would give you 9. Now you still have to do the problem like we've done before with your U substitution. The derivative of 4x is 4. And we're going to adjust not with a 1/4, but with a 5/4. Why would I adjust with a 5/4? Yeah, exactly, because the 4 is perfect. I can't say that any better. The 4's cancel, and then you get 5, which is in the problem. And then essentially you can write the answer. We identified it as arcsecant. You're going to have this 5/4 out front for the adjustment that we did. And then arcsecant does have that 1 over a in front of it. So it would be 1 over 3 arcsecant u over a plus c. And that one has the absolute value. Again, if you forget to put that, I'm over it. I'm just letting you know it's there. Also, if you want to multiply these fractions together, that would be 5/12, but you can even just leave it like that. And I'm fine with that. Do you remember this one? Is this coming back to you? Like remembering this sort of? Ooh, what did I change about this one? The definite, good vocabulary, definite integral. There are boundaries. So you're going to actually work it out and get a numeric answer. This one's arctangent. It doesn't have a square root. What is A going to be? 2. And U is just X, which is fantastic because the derivative of X is just 1. So du is dx, and then there's no like further adjustment that needs to be done. So that is good. So look at your arctangent pattern. It's 1 over a, so that's going to be 1 over 2, 1/2 arctangent u over a, which is x over 2, and then just don't put the plus c. Instead, we're going to have such that 0 to 2. We're going to do upper boundary minus lower boundary. So if it was free response, you don't have to simplify it down. You can just do upper boundary. If you plug in 2 here, you're going to get 1. 2 over 2 would be 1. So you'd have 1/2 arctangent of 1 minus 1/2 arctangent of 0. And again, if it was free response, you could stop there and that's a sufficient answer. If it's multiple choice, you have to keep going. And it's not that hard. You're just doing it backwards. You know how usually you're given the angle of the triangle and you find the sides? This time you have the sides of the triangle and you're finding the angle. So your answer should have pi in it. It should be like pi over something, all right? 1 is a little bit tricky. That's the triangle where both the sides are the same because anything over itself is what? Remember, tangent is y over x. Anything over itself is 1. So what is this angle? That's our goal there. Pi over 4. Good. All right. So this is 1/2 times pi over 4 minus, and then for 0, you're going to be right here at the point 1, 0. 0 over 1 would give you 0. Again, tangent is y over x. So that's 0 pi. You haven't rotated anywhere. So that would just be nothing. A lot of people will also just memorize tangent of 0 is 0. Kind of like sine of 0 is 0. So that part's gone. And this would be pi over what? 8. Good. So pi over 8 would be your like final completely simplified answer. We're going to do a couple more before I give you a break because of that drill. I'm going to try to keep going here. Oh, go ahead. So let me pause this. Hold on 1 second. All right, so for this one, we're going to have to split it into 2 separate problems. We're going to have one problem for the x. So we're going to put x over that denominator. And then we're going to have a separate problem for the -5 over that denominator. And what I would suggest is just put the -5 outside of the problem. I mean, that's personal preference. You can leave it in the numerator if you want, but that's my suggestion. Why, Ms. Cole? Why do we have to separate that? If you try to do a regular old U substitution, it will not match up. Remember how I said all the pieces of the puzzle have to be there? It's not going to work. You can try, but it's not going to work. And it also will not follow any of the inverse trig patterns that we just wrote up here. Notice none of these have a variable in the numerator. If you have an x in the numerator, it's not going to follow one of these patterns. So that x really messes us up there. Okay, so we split it into 2. Are we good so far? Splitting it. This one is going to be a regular old U substitution like we did last class. This one is going to be arc what? Tangent. Good, because there's no square root. So we're going to do 2 separate problems, and together it will give us our whole answer. So for this one, U is going to be that denominator. That derivative would be 2x dx. And then how will we adjust that? A half. Good. And I'll highlight. So in place of x dx, we're putting 1/2 du. So 1/2 goes out front, du goes at the end. What's still there that I didn't highlight? 1 over u. Perfect. And that antiderivative would be ln of u. So it'll be 1/2 ln of x squared plus 1. I'm not going to put the plus c because we're actually not done. That was only half the problem. Now we're going to do the other half, string it all together, and we'll put the plus c at the end of the entire thing. So for this one, a would be what? 1. Good, which is nice. This is 1. U would just be x, which again is great because derivative of x is just 1. Du would just be dx. So I'm going to write down here so I can string my whole answer together. It's going to be -5. And then arctangent has that 1 over a out front, but we get to kind of skip that. How come? Yeah, it would just be 1 over 1, which some people like to write just for the pattern. I wouldn't, but anyway, it's there, but it's just 1. So -5, arctangent u over a, that would just be x over 1, which would just be x. And then plus c for the whole thing, and all of this is your answer. So if you get something that won't work, you have to try something else. Like you have more tools in your toolbox now. So split it apart. You can do a regular U substitution for one of them, and then your inverse trig for the other one. All right, we'll do a couple more. I will give you a break, but let's do a couple more. And I'm sorry about that HVAC. You'll get used to that in the colder months. Like it does that constantly. It turns like it cycles and then it kicks on. It's real loud. I'm sorry. I have no control over them. But this room is generally a pretty good temperature, so I like to not complain too much. All right, so the issue with this one is it isn't in the correct format, like the correct pattern for one of our inverse trig functions. So we're going to complete the square. You have to remember this back from pre-calc, all right? But I'm going to remind you of it. So here we go. You write down the first two terms, and then it is divide by 2 and square. You're going to take this middle number, divide it by 2 and square it. Is that ringing any bells, sort of? Maybe once I write the answer, it'll like come back to us. But what would you add on? Good, 25, and then give it a hug. Put some parentheses around that. Do you guys remember me saying give it a hug? Now you have to turn a 25 back into a 34 because you can't just go around changing the problem. You have to maintain the integrity of the problem. So what are we going to add on? 9. Because 25 plus 9 will give you 34. And then the whole point of doing that, you ask, is you can write it as something squared plus 9. So what would go in that blank? Like if you factored it, it would be something squared. Good, x minus 5. You had a good pre-calculus teacher. Now it looks like our arctangent pattern. So we just had to rearrange it a little bit to get it to look like the arctangent pattern. So what would A be? 3, good. And U would be x minus 5. And that derivative would still just be 1. Which is nice because then there's not like an adjustment that you have to do. And then you can pretty much write out the answer. It's 1 over A, so it'll be 1 over 3 arctangent U over A plus C. I'm going to have you guys try one like that, and then we'll do a break. I want you guys to try it, and then I'll give you the answer. Or we'll go over it together. All right, so what did you add on to complete the square? 9, good. And then at the end, you'll have plus 4, good. All right, so that will be something squared plus 4. And so what is the something? X plus 3, good. So A would be 2, U would be X plus 3, du would be dx. To be honest, the thing that trips people up on the test about this is like, are you starting to do it in your head? Like where you can almost just like, okay, make sure you write enough for me. Because I get people that will almost write nothing and then just put the answer. And if it's wrong, then I have trouble with the partial credit. So please write, do some work for me, all right? It'll be 1 over A. So 1 over 2 arctangent U over A plus C. Well, I can see it. This is another one where we're going to complete the square. There's just a negative in it, which negatives are difficult. Negatives are the most commonly missed thing ever because they're just slippery little devils. All right. So we are going to pull the negative out, but just from the first two terms, because we're going to adjust for that last number anyway. Exactly like we did in these ones. Remember how we didn't really worry about the 34? We just adjusted for it at the end, and we didn't really worry about the 13. We just adjusted for it at the end. It's going to be the same thing here. So we're going to take the negative out of just these two terms, which is going to turn them both positive. So it'll be x squared plus 4x. And then you want to complete the square. So you divide by 2 and square. And so what would we add on when we divide by 2 and square? 4 is a little bit weird. Everyone's always like, well, it's 4. That's because 2 plus 2 is 4 and 2 squared is 4. So it ends up being 4. Here's the tricky bit. It's not really a 4. It's really a negative 4 that you have to turn back into a 5. So you would add what? 9, good. Let me lengthen all of these here. -4 plus 9 equals 5 is what we did there. The whole point of that, and you're like, why on earth are we doing this? It's so you can write it as something squared. Now I'm also going to write this the other way around so it follows the pattern. I'm going to write it as 9 minus the rest of this. So it'll be 9 minus what squared? What will go in the blank there? X plus 2, sweet. All right, so is it arcsine, arctangent, or arcsecant? It is arcsine. So you have to rearrange it to get it to look like the pattern. A is 3, U is X plus 2, and so du is just dx. The issue with like this unit and the next one too is you get so many methods for how to integrate things that the trouble becomes you have to be able to look at a problem and go, oh, what tool in my toolbox am I going to use to get through this? That just comes from drill and practice. You kind of just have to do a lot of problems until you get used to it. All right, arcsine does not have the 1 over a out front, so do not put a 1/3 there. It'll just be arcsine u over a, so x plus 2 over 3 plus c. So that's completing the square. And you do that in order to get it to look like one of these 3 patterns. All right, the last method that we're going to look at is synthetic division. That's okay. I taught it to you, and I'm going to review it with you right now. I stuck boundaries on this one as well, just for extra fun. And when you evaluate the boundaries, what does it tell you? Area under the curve. Oh, let's review what a derivative is, because calculus is really derivatives and integrals. An integral is area under the curve. What's a derivative? Wonderful. Instantaneous, that was the other one. Nice, cool, you got it. All right, first you decide what makes this 0. 1 goes in that little box off to the side, and then you thief all of the coefficients from the problem, but your countdown has to go in order. So do you remember this? 3, 2, 1, 0? All right, this one's good. 3, 2, 1, 0. So you're just going to take all of the coefficients. So it'll be 1, -3, 5, -3. This is actually what we're doing in pre-calc right now, so it's kind of cool. Like I'm seeing all the connections. You bring down the first number, so this 1 comes down, and then you multiply, add, multiply, add, multiply, add until you get to the end. Okay, maybe just watch me do the first one. 1 times 1 is 1. Add the column, you get -2. And you're going to do it again. 1 times -2 is -2. Add the column, you get 3. I'm seeing heads nodding. This is coming back to us, sort of. 1 times 3 is 3. Add the column. I made the first one come out to a 0 remainder to make the first one that we do a little bit easier. Okay. Now you're going to take that and put it back into the integral. You start with 1 less than the power you had. That's because you divided out an x. So you have 1 less than you had before. And then you follow your countdown. It's going to be x squared minus 2x plus 3. And then you can do the antiderivative of that, which is a whole lot easier than trying to do the antiderivative of this thing. That's the point, is you made it look a lot simpler, right? So what is your antiderivative going to be? 1/3 x cubed minus x squared plus 3x such that 1 to 2, and we're going to do upper boundary minus lower boundary. So plugging in the 2 cubed is 8, so that'll be 8/3 minus 4 plus 6. And then lower boundary, if you plug in 1, you would have 1/3 minus 1 plus 3. I'm going to stop there, but if it was multiple choice, you understand you would have to negotiate your way through that until you got an answer. Remember that one in your homework last time that was 16 over 15? You had to figure it out. We're just going to try that a couple more times to make sure that it's sinking in. Because when you look at a problem like that, how on earth would you get an antiderivative? You know what I mean? Like that's when you look at that, you need to go, oh, I need to divide that out, because how else would you get the integral? Like how else would you go backwards? Yeah, I mean, like I don't even know. Like that's how you get through it. So what number would go in the little box off to the front? -3. It's whatever makes that denominator 0. And I will go ahead and tell you this countdown is not in order. We are missing something. And you have to put a 0 for what you're missing. So what are we missing? Yeah, the x to the 1. So that's missing. So good, you guys are already saying it. 2, 4, 0, -5. Go ahead and divide it out. I will tell you though, this one has a remainder. It doesn't make the problem any harder. There's just an extra number at the end. It's not any more work if there's a remainder. There's just like one extra thing you have to write, that's all. But there's not like any extra step. Did you get 2, -2, 6, -23? Okay. Oh, I don't know. You probably missed a negative. I would bet money. It is always a negative. That's like almost always what it is. Oh yeah, you always have to bring down, and maybe if you put an arrow there, sometimes that can help you remember. Oh, like on this, yeah, this one was a little bit weird because they were all 1. Maybe draw an arrow. All right, so when you put it back in the integral, you're going to start with x to the what? 2, good. So it'll be 2x squared minus 2x plus 6. And here's how you do the remainder. It will be minus 23 over the x plus 3. What you're essentially saying is we were unable to divide out that part. It's remaining. It is left over. So it stays over the x plus 3. Now we do the antiderivative. This is like the only step that's calculated. But now we have something we can do an antiderivative of. This would be 2/3 x cubed. You would want to do 1/3 x cubed, but there's 2 there. 2/3 x cubed minus x squared plus 6x minus, pretend it was just an x. What's your derivative of, well, I know there's a 23 there, but what's your derivative of 1 over x? ln. It's just that it's going to be x plus 3 instead of just x. So it'll be 23 ln x plus 3. And then plus c to finish it off. That's like the cherry on top. We will just do one more. That's all I have space for anyway. I know you're like, she's making us do all these problems, but you know what? I can't just do like 1 or 2 and be like, oh, we're done. You know, you have to do a few in order for it to sink in. And if you feel like you've got it and you work ahead of me, that's cool. What number is going to go in the little box? 2. This countdown is in order, isn't it? 3, 2, 1, 0. So you can just go ahead and take the coefficients. There will be a remainder, but that's okay. It's not any extra work. You just kind of tack it on at the end. I drew in the arrow that time, so hopefully that helps. You should get 4, 7, 16, 31. Sounds like I'm calling out like lottery numbers. But I'm not hearing any complaining, so I'm assuming that one okay. Okay, so we're going to start with x squared, 1 less than we had in the first place. So 4x squared plus 7x plus 16. And then the 31 stays over the x minus 2. Again, what we're saying is we were unable to divide that part out, so it stays as a fraction. Spoiler alert, that'll be ln. So your antiderivative, this is like the one step that's calculus. 4/3 x cubed plus, ooh, what will this one give us? Good, Good, perfect. Plus 16x plus 31 ln x minus 2. Oh, bummer. Plus c, had to go down. I know, right?